Okay, so this video is going to be going over one of the problems that we had for classwork on the 18th of January. So this was on Friday. So let's go ahead and get started on this problem. I want to make this video relatively brief. So in this problem, what you're told is you have a rock and you're throwing the rock directly upwards and you're at some height of h above the ground. You throw it up with some initial velocity v0. And what we want to do is we want to start from the acceleration being given of minus g, where g is the acceleration due to gravity. We want to derive the kinematic equations that describe the situation. Okay, so let's go ahead and get on into it. So to start by deriving these equations, something that's helpful for all of these problems is to kind of go back to our first principles. What's always going to be true in these kinds of problems. And so what I'm going to lay out is what's always true. So if you want to go from, let's say you have your acceleration at the top, your velocity in the middle, and your position. Now you could call this y of t or x of t, depending on your coordinate system. Are you moving up and down, then you usually call it y. You're moving left and right, you usually call it x. But either way, we're interested in going up from the bottom, or we want to go down from the top. And so we know the relationship between the position and the velocity is going to be such that the velocity is going to be the time derivative of the position. And so that's to say, if I want to start at the bottom here, so if I want to start at the bottom and work my way up one step here, what I do is I say that the velocity is related to the position via, I'm going to write it off to the side over here. This says that v of t is going to be equal to dx dt, or dy dt. Eventually, when we get into two-dimensional motion, we're going to have both of these. We're going to make these a factor. So what that's to say is if I want to go up from the position up to the velocity and the acceleration, then this is going to be taking a derivative. Now, if I want to go the opposite way, that's going to be just the antiderivative. So if we want to go from acceleration to velocity or from velocity to position, we do the antiderivative. And the last equation that I need here to make this true in general for all of the problems that we're going to consider is just to say that a of t is equal to dv dt. Okay? And this, we can put a nice box around this. These are all the equations that you will ever need for one-dimensional motion. Okay, so now let's go ahead and apply it to this particular problem. And so in order to do that, what we're going to say is we know that a of t, this is part A, we know that a of t is equal to minus g. We want to find our kinematic equations. So we're starting all the way at the top here. We're starting up here. And we want to go down. Okay? So in order to do that, what we're going to do is we're going to say that v of t, or dv dt, is going to be equal to a of t. And so then what we can do is we can say, okay, if we want to find v of t, then all we need to do is say v of t is going to be equal to the integral of a of t dt. Because really, if you want to connect this all the way back to the fundamental theorem of calculus, this is just saying that this is the integral of dv dt dt, right? Because we know that a of t and dv dt, they're the same thing. That comes from this definition right here. Okay? So now all we need to do is we need to evaluate this for the particular function that we have here. And so this says that this is going to be equal to the integral minus g dt, right? Because our acceleration is just going to be minus g. This is going to give us minus g times t plus a constant of integration, right? So this is really important, and this is where people can tend to make a mistake. They'll forget the constant acceleration, or the constant of integration, or they'll leave it out. So let's kind of summarize what we have for now. This says that v of t is equal to minus g t plus c. Okay. Now, this constant of integration is still undetermined, and so what we need to do is we need to determine it for the situation that we have. And what we can do is we can use some conditions that we're given. So we're given up here that our initial velocity is going to be v0. So when we talk about an initial velocity, what that's really telling us is what v of t is equal to 0 is. Okay, so this is the velocity when you evaluate the time for t is equal to 0 seconds. It's like when we're beginning. Okay, so this is going to be equal to the v0 that we were given in the statement of the problem, and it's also going to be equal to this function that I have above here. So this function evaluated when the time is 0. And so that's just to say that this is going to be equal to minus g times 0 plus c. This term goes away, so that's 0. And then this says that v0 is equal to c. And so in the end, what we have is that our first kinematic equation says v of t is going to be equal to minus gt plus v0. Now, you might think that I'm going through a whole bunch of extra steps here to show this. Why not just start with this equation? Well, this equation is not true in general. This equation is only really true for two things. First, if I know that I have a constant acceleration, and second, if I know what v0 is or what the initial velocity is going to be. But we're not always going to have those pieces of information. That's why I'm going through this process of showing the whole thing in general, because this approach is always true. It's just the pieces in between might be a little bit different. Okay, so let's keep going. Now, because we have, we're talking about something vertical, okay? I'm going to talk about y of t instead of x of t, right? Because typically when we talk about x and y, x is horizontal, y is vertical. And so here, to get my position equation, I'm going to say that v of t, or sorry, dv dt is equal to, oops, that's a mistake. Now I'm going to say that dy dt, sorry, is going to be equal to v, which is equivalent to saying that y of t is going to be equal to the integral of v of t dt. We have what this is right here, so we can just take it and we can plug it into this equation here. When we do that, that says that this is going to be equal to the integral minus gt plus v0. Let's put our parentheses here. Don't forget our dt. And now we have another integral that we can evaluate. When we evaluate this integral, we say that this is going to be equal to, sorry, I don't have an integral sign anymore. This is going to be equal to minus 1/2 gt squared plus v naught t plus a new constant of integration. Okay, so here's our y of t. We just need to evaluate for this constant of integration. Okay, now I'm a little bit in the way here, so I'll try to move this over a little bit. So let's grab this guy and slide him on over. Okay. So I'm not in the way anymore. So now we have to evaluate for this constant of integration. Again, in order to do that, what we're going to do, we go all the way back up to what our initial conditions are. So we know that the first initial condition we used was for the velocity. The second one has to do with the height, right? So we know that we're at some height of h when we're starting here. Okay, so coming on back down here, what we can do is we can say that y of t is equal to 0. It's going to be equal to h, which is equal to minus 1/2 g. Evaluate everything at 0. b 0, 0 plus c. This guy goes to 0. This guy goes to 0. And what we're left with is that h is going to be equal to c. And so our final kinematic equation, and I'll summarize all three of them in just a second. This one says that y of t is equal to minus 1/2 gt squared plus v naught t plus h. And let's just kind of collect everything in one spot. We have our velocity equation, v of t is equal to minus gt plus v0, and our acceleration equation, a of t is equal to minus g. You can put a box around that, and that is the answer to the first question. Okay. Now, like I said, you might think I'm going through some rigmarole to go through this whole process, but this process is true in general. This just happens to be the simplest case. Okay, so let's go on back up here to see what our next question is. So the next question says, explain verbally and mathematically what it means for the object to reach its maximum height. Think about your functions. What condition could you apply to one of them? Okay, so for B, we know that at maximum height, I'm going to close this window because I'm running something in the background that's slowing my computer down right now. Okay, I don't have to drive that monitor at all. So we know that at maximum height is when it starts to turn around, right? So we're going up and up and up and up and up, and then we start to go down. So what this tells us is that at maximum height, the velocity, v, is equal to 0. And I'm going to be very explicit here. I'm going to be very explicit when I write this. So the velocity at some time evaluated at the maximum height, so there's a specific time corresponding to when I get all the way up here, that's equal to 0, okay? And you'll see why I'm going through this in a second, okay? Now, this is the mathematical side is right here. This is the verbal side of the velocity is 0. There's still a third way to say this, and that's to say that dy dt is equal to 0. Okay? Evaluated at t is equal to t max. Okay? Now, all three of these are equivalent, and we can see why they're the same thing. Okay. Good. So let's go back on up to the top. I don't remember what my question was asking still. Find the time it takes to reach the maximum height, call this T max. Okay. So now we want to find the time it takes to get to T max. And we can apply that condition to one of our derived kinematic equations, namely the velocity equation. So when we look at the velocity equation, when we want to evaluate this, all right, this is going to be part C. This says that v at t is equal to t max is equal to 0, which is going to be equal to minus g t max plus v0. Okay. Now we just have to do a little bit of algebra to get ourselves to just what t max is going to be equal to. We can move this guy to the other side of the equation. We can divide by g, and what we end up seeing is that t max is just going to be equal to v0 divided by g. Okay. Now, I do want to pause here for a second and talk about something that might be a little bit confusing to you. When I'm using notation, there's a very good reason why I'm using the notation that I am, and a lot of times students have a difficult time discerning the difference between this and this. What is the difference between t and what is the difference between t max? And put very simply, T max is a value. This is a value. So it's how long does it take to get to the top? That's a number. Like we could if we were running a real experiment and we had values to play with, we could say T max is 5 seconds, T max is 10 seconds, but it's a number. Whereas T is a variable. So t is the input parameter I'm putting into the function as this is moving. Okay, so little t just by itself is a variable. T max is a value. Okay, good. So now let's go on back up here. See what my next question is. Find an expression for the maximum height in terms of T max. Okay, so if we want to find the maximum height in terms of T max, what we can do is we can go to our position equation. So our position equation, which was right here, is going to say, and I'm going to just write it again down here, that y of t is going to be equal to minus 1/2 g t squared plus v naught t plus h. Okay, so this is part D, I believe. Part D. Okay. So if we want to write this in terms of T max, what we would do is we would say y of t is equal to t max is going to be equal to, let's give this a name too. Let's call this y max. So the maximum distance, or the maximum height in y, is just going to be equal to minus 1/2 g t max squared plus v naught t max plus h. And we can even take this t max and plug it in to our function, because we know what t max is algebraically now. We know it's just v0 over g. And then what we do when we see that, and there's a little bit of algebra here, so if you don't follow this, make sure that you do it yourself. This says that this is going to be v0 squared over 2g plus h. Okay. Y max is equal to this. Perfect. Okay. Now, it looks a little bit funny, so let's go ahead and check our answer with dimensional analysis. We might still have some terms wrong here, but or some numbers like the 2. The 2 might not be right. I promise that it is. Like I said, you should check it. But we can check this with dimensional analysis. So we can ask ourselves, what should the units on the left-hand side be? So this is using our tool of make sure the equal signs are the same. This is using dimensional analysis to do that. So what are the units of y max? Well, y max has units of meters. Okay. What are the units of h? Units of h should also be meters. What are the units of v0 squared over 2g? Well, if we did this correctly, and I'll leave that as question mark, this should also be meters. Well, let's check it. So the units of v0 squared are just going to be equal to the units of v0 quantity squared, which is just going to be equal to meters squared over seconds squared, right? Now, let's see what happens when we do, well, let's also, for the sake of completeness, say the units of g. These are going to be meters per second squared. And so we can see that the units of v0 squared over g are going to be meters squared per second squared divided by meters per second squared. And so seconds cancel. And let's do this in a different color here so we can see the cancellation. So we're going to cancel this, cancel that, cancel 1 power of that, and what we're left with is meters. So this is our dimensional analysis. Very, very important tool. You should use it after every problem that you solve, or every step that you're solving a problem. And it might seem a little bit cumbersome at first, but I promise you'll spend a lot less time. You'll waste less time if you check your work as you're going, as opposed to getting all the way through a problem, having something wrong, and not realizing what it is. It's always better to check yourself as you go. Okay, so that's finding the maximum height. Don't remember what the next question is. How long does it take for the rock to fall from the maximum height? So now there's a couple of ways to do this, and one way to do this is actually just to start your watch again when it's at the maximum height and say, well, if it falls, well, how long does it take to fall to the ground? Okay, so we know what y max is. We know what y max is. Y max is this. And so what we can say then is that, what if we have some new function? What if we say this should be part E, I believe. Check. Yeah. What if we had some new function? Let's start our watch at the top, and we say that y, let's call this y star, just to denote it's different than the y of t I had before. Y star can be written as y max minus 1/2 gt squared. Okay, it has no initial velocity; it's all the way at the top, and then you let it go. Okay. V star of t is just going to be equal to minus gt. Okay, because there's no initial velocity, right? I kind of picked off the terms that I didn't need. All right. So what we were trying to do is we were trying to find how long it takes to get to the bottom. And so in order to do that, what we can do is we can say that time is the time that it takes for this function, y star of t is equal to t fall, or the amount of time it takes to fall. And this is going to be equal to 0, right? Because we're saying that it's going to fall from up here, it's going to come down here, and then its height is going to be 0. And so this is going to be equal to y max minus 1/2 g t fall squared. And again, we can do a little bit of algebra, and I'll leave this to you as an exercise. Hopefully I won't make any mistakes. I'm sure you guys will let me know if I do. T fall is going to be equal to 2y max. Let's make that a subscript, so that's 2y max divided by g square root. And again, we could do some dimensional analysis here to see if you believe me or not. Okay, so let's use our tool. So what are the units of y? Units of y. So let's do our dimensional analysis a little bit quicker here. What are the units of y over g? These are going to be units of meters divided by meters per second squared. Okay. Now, when we do this, this is the same thing as meters times seconds squared over meters. So this has units of seconds squared, but don't forget that we're raising this to half power, right? So when we do this, this says that this to the half power is going to be this to the half power, this to the half power, which is just going to be equal to a second, which is what we expected to be. Okay, dimensional analysis, very important tool. Make sure you use it. Okay, so we found T fall. The next thing that we want is now we've done all this analysis. Now we can plug in some numbers. So we want to find what the maximum height is if the initial velocity is 20 meters per second. The height is 1 meter and g is equal to 9.81. I'm going to be lazy because I don't want to use a calculator. And I'm going to say that this is going to be equal to 10 meters per second. Right. Okay. Just as an approximation. It'll get you there. We want to find the maximum height and the time that it takes to get to the ground. Okay. So F. So we want to find the maximum height. Well, we already did the analysis here. We can say, well, gee, y max is just going to be equal to v0 squared over 2g plus h. And so what were the values that we had here? Now is when we plug in numbers. Don't plug numbers in before this because you can make mistakes. So now let's plug our numbers in. So this is going to be equal to 20 meters per second squared divided by 2 times 10 meters per second squared plus 1 meter. Okay? So this right here is going to be just 20. So I can cancel a factor of 20. That's kind of nice. We have 20. The units here, when I do this, I'm going to be a little bit lazy, but you'll end up seeing that these units for this first term are going to cancel, so this is just going to be 20 meters. Okay, this is going to be 20 meters plus 1 meter, and so that tells us that at least for the approximation for our velocity, or sorry, for our acceleration being 10 meters per second squared, this says that this is going to be equal to 21 meters. Okay. Now, let's look at, so this is the first part. And I don't remember what the question is, so I apologize to you guys, I have to scroll up. Find the time it takes to hit the ground. Okay, again, we can use what we found in a previous part in order to determine that. So we want to find what T fall is. So I already set this up, so T fall is going to be equal to the square root of 2 times y max divided by g. And so again, for the sake of just doing an approximation, this is going to be the square root of 2 times 20 meters divided by 10 meters. And so this is going to get me, this is going to be about equal to 4 seconds. Okay. You can see that because I can cancel. Factor at 10, that gets me 2. I'm missing some units here, but yeah, it gets us 4 seconds. So it turns out that I was lucky with the numbers that I chose, so these all ended up working out really nicely. Okay, so that's how long it takes to fall. Okay. Now the last part is just to plot all of this, I think, and you could compare T fall and T max, but I'm just going to plot it, and you're going to see exactly how they're going to compare. Okay, so let's start with our equation for x, or in this case, our equation for y. We'll start here, okay, and then we'll plot it from there. So this is part G. Part G is to part G is to do the plots. So if we looked at y t, this is t. Well, what does it look like? Well, it's going to be going up and up and up, and then it's going to go down. But it started at some height that's above the ground, right? That's what that h is telling us. So this is going to look like that roughly. Okay, this should be parabolic. It's a function that's y of t is equal to minus 1/2 gt squared minus or plus v0t plus h. That's what we're plotting. Okay. Now I didn't tell you exactly what v0 and h were until the very end, but you don't really need to know what the values are to know what the plot is roughly going to do, provided that you make some assumptions about h being positive, v0 being positive, and then that's the kind of plot that you're going to look like. Okay, that it's going to look like. Okay, so now let's look at our velocity, or velocity v of t. Is just going to be the plot of the slope of this. Now, if we look at the plot of the slope, we see something kind of interesting here. So I'm going to draw the slope in at a couple of points. So that's the slope there, slope there, slope there, slope there, slope there. And so this should be getting a little bit steeper. I sketched it really quickly, but this should be doing something a little bit more like that. Okay. You guys will forgive me for my poor artwork, I'm sure. Okay, so if we're plotting the slope, it starts with some positive value, right? So this is a positive slope. This is a positive slope. There's a slope of 0, then it's negative, and then it's negative. And it's going from large values where it's steep to more and more shallow until it's 0, and then it goes down. And now, if we look at the function for v of t, this is just going to be equal to v0 minus gt. Okay. Now, don't be scared by the fact that these are different variables than you might be used to seeing. This is really exactly the same thing as y is equal to mx plus b, where b is some positive value and m is negative. So what is this going to look like? Well, if I lined it up exactly with this one, let's draw some dotted lines down here. This should intersect the y-axis, or sorry, the t-axis right there, and then this is just a line. Okay. Now, the last one is just plotting the acceleration. So if we look at the acceleration, a of t is just going to be the slope of this. Okay. What's the slope of this? It's just some constant, and it's also a negative constant. And so this is going to be this is going to be minus g. Okay? And if we were doing some experiment, we would see that this is minus g is going to be equal to minus 9.81 meters per second squared. Okay? And that's going to be it. So I'll see you guys in the next video.